All right, let's remind ourselves of the equation of our model here. So remember, it was percent change in House seats for President's Party equals negative 6.71 minus 1.00 times the unemployment rate. So there is a negative slope in the line. However, this slope and the y-intercept are only estimates of the parameter values. We might wonder, is this convincing evidence that the true linear model has a negative slope? That is, if the null hypothesis says beta 1 equals 0, meaning the true linear model has a slope of 0, and the alternative hypothesis is beta 1 is less than 0, or in other words, the true linear model has a slope that's less than 0, the higher the unemployment, the greater the losses for the President's Party in the House of Representatives. So just like the other point estimates we have seen before, we can compute a standard error and a test statistic for B1. We will usually label the test statistic using a t, since it follows the t-distribution. We will rely on statistical software to compute the standard error and leave the explanation of how this standard error is determined to a second or third statistics course. The table below shows software output for the least squares regression line. The row labeled unemployment represents the information for the slope, which is the coefficient of the unemployment variable. So this first column where it says estimate, these are the point estimates. Okay, in this column where it says t-value, these are the test statistics. And then this column where it says PR, these are the p-values. So for each row of this table, we have a set of hypothesis statements. So for the first row, we would say that the null hypothesis is that beta 0, or the y-intercept, equals 0. And the alternative hypothesis is that beta 0 or beta naught does not equal 0. And for the slope, we have the null hypothesis, beta 1 equals 0. And then we said earlier that the alternative hypothesis is that beta 1 is less than 0. So we're looking at a one-sided p-value, or a one-sided hypothesis test here, whereas we have a two-sided hypothesis test for the y-intercept. So that's just for this particular scenario. So remember that the equation is the percent change equals negative 6.71 minus 1.00 times the unemployment rate. Here's example 2. What information is given in each column? Okay, well, we talked about how this first column gives us the point estimates. The t-value column gives us the test statistics. And then the final column gives us the p-values. And if you use a TI-84 calculator, these come from the tcdf command. For test statistics, the formula is the point estimate minus the null value divided by the standard error. So this would be negative 1 point for the slope, the second row. This would be negative 1.0010 minus 0 divided by negative 1. Oops, sorry. Divided by the standard error, which is 0.8717. And that gives us approximately negative 1.15, which you see here. Okay, and then for the second row, the tcdf command, we would put in negative 999, comma, negative 1.15, comma, and then the degrees of freedom are 25. It tells us that right here. And we're doing a one-sided p-value, remember, for this part. That gives us about 0.131. Now, if we did want a two-sided p-value, remember that the t-distribution curve looks much like a normal curve. The center is at 0, so here's about negative 1.15, and we measure all the area to the left. That's the one-sided p-value. If we go equal distance on the right and measure that tail, then the two-sided p-value, 2 times tcdf, of negative 999, comma, negative 1.15, comma, 25, we would get 0.2610. Okay, and that's the value that you see here. So because ours is a little different than theirs, and that's just due to more rounding, since we rounded negative 1.15 as our test statistic. They also rounded it that way, but when they did their calculation for the p-value, they did not use the rounded version of the t-value. We did, and that's why our answer is a little bit more rounded than their answer. Okay, so once again, we're going to talk about the test statistic. So we previously used a t-test statistic for hypothesis testing in the context of numerical data. Regression is very similar. In the hypotheses, we consider the null value for the slope to be 0. So we can compute the test statistic using the t or z score formula. They're the same formula. Point estimate minus null value divided by standard error, and we showed that that's how we got negative 1.15. Once again, for the p-values, if we wanted to give a two-sided p-value, we would have the alternative hypothesis beta 1 not equal to 0 instead of less than 0, and then we can verify that by using the tcdf function, and we make sure and multiply our result by 2 to get the p-value of 0.2610, which is again a little different than what they got because of rounding of the t-value. Example 3 says use the table to identify the p-value for the following hypothesis test. So when we want to just test when b1 is less than 0, not when b1 is not equal to 0, that's when we have the one-sided p-value that we calculated earlier. So we can either do our tcdf formula and not multiply it by 2, or we can just take the p-value, the two-sided p-value that's given here, and divide it by 2. That gives us about 0.13085. In either case, we would still fail to reject the null hypothesis because this number is greater than 0.05. All right, here's example 4. Suppose for whatever reason we wanted to test the hypotheses. The null hypothesis, beta 1 equals -1, and the alternative hypothesis is beta 1 is not equal to -1. So instead of using zeros, we're using -1s. How would the test statistic and p-value for the slope change? Well, here's the new test statistic. You would take the point estimate minus a -1 this time, divided by the standard error, and we get -0.001147. So if we draw out the t-distribution curve where 0's in the middle, -0.00, so that's going to be really close to 0. It's on this side. So we would be shading in that tail. So this is where -0.001147 would be. And we would put, so we would also go to similar to the right hand side of 0 and shade that part in for a two-tailed p-value. So we would go 2 times TCDF, and then we would go -999, comma -0.001147, comma 25 degrees of freedom, and we would get approximately 0.999. So this is a very large p-value because it's almost 1. It's almost 100%. So that means we pretty much have no evidence that the alternative hypothesis is not equal to -1, and we would fail to reject the null hypothesis. Okay, example 5. Create a 95% confidence interval for the slope. Do the results agree with your conclusion in the previous problem? So we would have to look up on a t-distribution table to find our t-star value, or our critical value for the t-distribution, using 25 degrees of freedom and a 95% confidence. And that number ends up being 2.06. So again, that's from the t-distribution table. So you'll need to go back to that handout to find it there. And then we have our equation, -1.0010 plus or minus 2.06 times 0.8717. So this is the 95% confidence formula. We take our point estimate plus or minus the t-star value times the standard error. That's the formula. So when we use the minus sign in that formula, we get the lower value. So we get our 95% confidence interval. So when we use the minus sign in that formula and calculate that out, we should get a value of about -2.80. When we use the plus sign in that formula and calculate it out, we get about 0.795. So this is a very large range of values. So, in other words, we would fail to reject the null hypothesis. Again, that matches our conclusion last time. We have an indication that the data is just all over the place. But remember, the reason we fail to reject the null hypothesis is because the null value is inside the confidence interval. So if our null value is still the -1, it's in the confidence interval. Even if our null value was the original 0, it's still in the confidence interval. So that means we failed to reject the null hypothesis. Okay, example 6. The data for the Great Depression, 1934 and 1938, were removed because the unemployment rate was 21% and 18% respectively. Do you agree that they should be removed for this investigation? So here's what it looks like with the outliers removed, and here's what it looks like with the outliers included. So we might say that yes, we agree. There aren't any unemployment rates that even come close to those rates in any other year. So you can see with the outliers removed, we have a -1 slope, and with the outliers included, we have a positive 0.037 slope. So they're vastly different. So one more caution about p-values. Just as a reminder, the last column in the regression output often lists p-values for one particular hypothesis. It is a two-sided test where the null value is 0. If your test is one-sided and the point estimate is in the direction of the alternative hypothesis, then you can just cut in half the software's p-value to get the one-tail area. Otherwise, be cautious about using the software output to obtain the p-value.